So our first thing is to calculate work. And in physics, and this is going to be a joke that I hope you guys will really appreciate, okay? I think it's funny, but maybe you won't appreciate it, is that work is a transfer of energy. So if I do work on something, I'm giving it more energy. The best example is this. I'm doing work on this thing. Yes? Does it now have more energy than it did before?
Yes.
Yeah, I think so, right? We could attach this to a clever system of gears and levers and generate electricity, or maybe we could have this inside a clock, and as it fell, it could make the clock pendulum swing and the little cuckoo go out and all that stuff. Yes? Okay. I also could exert a force over a distance on this ball. It is now not moving, right? And I just exerted a force over a distance, right? Okay. Somebody's going to walk by, right? Okay. And I gave this thing energy, yes? It had the ability to surprise somebody out in the hall. Let's just say the least. Ooh, right? You know, there we have it, right? And when I've been doing that, by the way, I've actually been sitting there throwing the ball out the door. And sometimes people will come and they'll kind of peek in the door, like, what's going on, you know? Because they want to walk by, but they don't also want to get hit by a Nerf baseball on the side of the head. So there we have it. So this is our formula. They give it to us as like this. Work is F times S times the cosine of the angle between it. And the reason for this is, the reason that it's that way is that if we had a force that was like this, okay, and it had some angle between the force, so this angle here is the angle between F and S, and for this thing, let's presume that this sled slides along the horizontal, right? And so this force actually has two components. It's got a component straight up. Does the sled move straight up? Well, let's assume it doesn't, right? It does not move straight up. So the sled does move along the horizontal. And so what this does, what the cosine of the angle does is, if F is the hypotenuse, F cos theta is that component, right? And so what the cosine does is it gives you, it's the sense of how much of that force is in the direction that you move. Does that make sense? Does it also make sense that we haven't done any work on an object if we don't make it move? Does that make sense? Like this mass. If I try to lift it but don't lift it, have I transferred any energy to it? Now I'm thinking that trying doesn't count, right? I'm pulling on it. It's not enough force so to lift it. I have to actually make it move, yes? Okay, to do work on it. So that's one of the tricky things, right? And so if we've got some displacement like this, we just want to take that component. This component does no work at all. Okay, and then you know, let's do an example of this, right? Let's say I exert 6 newtons of force for 3 meters, right? The work, and let's assume that they are parallel to each other. Cosine of 0 is, it's either 0 or 90. Which one is it? Or 1. Which one is it? Cosine of 0 is 1, yes, and they're in the same direction, okay? So if the angle here is 0, oftentimes they don't give it, okay? They'll just say they push that in some direction, right? They won't give the angle. That means it's 0, that it's in the same direction, right? When they start giving angles, then you want to put the displacement and the force tail to tail and look at that angle right there, okay? So 6 newtons in the direction of 3 meters is 18 Newton meters of work, yeah? Okay? And you can also say that it's 18 joules, yeah? Or you can be sort of casual and abbreviated J, or you can be British and say joules. I believe they say jowls. I picture sort of jowls. Are you picturing that? You know, like one of those dogs, like a bloodhound or something. Are you picturing that? I don't know. Okay. And then of course, the funny story was that I taught this lesson actually as a senior, I think, in college. I was taking one of these classes, like, do you want to be a teacher kind of a class? Yeah. And I was sort of job shadowing this guy that was this physics teacher at a high school just down the road. And Gordon Risch was his name. And he was just a fantastic teacher, but he let me teach this class. Now picture I'm wearing threadbare corduroy pants. Not because I'm poor, just because I had threadbare corduroy pants and that's what I wore, right? Picture a big beard, big granola beard. Are you picturing that? Bushy, right? Okay? And I'm sitting there and I'm all nervous and I'm teaching this, right? And I write this word on the board, but I do not pronounce it. And some kid sitting back there goes, how do you pronounce that, right? And I said, it's jewels, like family jewels, right? Now, yeah, there we go, right? Okay. And what I meant to say was crown jewels, and I was picturing the crown jewels, yeah? Meant to say crown jewels, said family jewels, right? And of course you guys just laughed at me, right? Because there we are, right? But that's like, this is like the first day of class for me. I'm teaching this lesson, and these kids all are very nervous, and I'm nervous, and so there's lots of things you could do. You just laugh, and go, oh, I meant crown jewels. That's sort of funny, right? Okay. Or the other thing you could do is you could pretend that you hadn't just said family jewels, right? And I did a quick analysis of the situation and decided to go with the latter, okay? And then they, for their part, pretended that they weren't laughing at me, which was somewhat more difficult on their part, okay? Because it was like it became then a forbidden laugh. Like the laugh you get at like a wedding or God forbid, a funeral, right? of somebody that you don't know too well, possibly, right? And you deeply know that you shouldn't laugh, but there you are laughing, yeah? Nobody knows what I'm talking about. Yeah, the forbidden laugh, right? It's like convulsions. I think in middle or junior high school, we went to some fancy Stradivarius concert and got into one of the viola players, I'm very sorry, okay, did this thing where when you get to the end of a phrase, he would go, and then go forward, like this. And they were very good, but the sniffing just got to us. And where are we? Joules. All right. Newton meters. Okay. There are some tricky bits. Are we ready for the tricky bits? Okay. Tricky bit number 1. Okay. I think we've already done tricky bit number 1, and that is that if we don't actually make the object move, there is no way that we could have transferred energy to it. So if S is 0, even though there's an F, something times 0 is 0 work, because the notion here is that it's a transfer of energy. And then the other tricky bit is that if they are in the same direction, the angle between them is 0. Yeah? So if the force is this way and the displacement is this way, the angle between them is 0. But what if the force is this way and the displacement is that way? Well, what's the angle between them? 180. And the cosine of 180 is? -1, which means we did negative work. What does that mean? Well, what does it mean to transfer negative energy to something? It means it gives you energy, yes? Okay. Let me give an example of this, a very simple example. Okay. If I push this thing up at a constant speed, the force I'm exerting is which way? Which way is the force? Up. And which way is the displacement? Up. And they are both co-upular, yes? Okay. And so the angle 0, and that's positive work, yes? I'm definitely transferring energy to this thing. How about if I lower it at a constant speed? Which way is the force I'm exerting on it? It's moving down, but which way is the force? You don't want to see me exerting a downward force on this, right? That's like me slam dunking it into the floor. If I move it down at a constant speed, I have to exert an upward force on it, yes? Okay, so the force is up, displacement is down. Okay, that's the best example of negative work that I can think of. Yeah, there could be. You could do something with a pulley that would be negative work. But this is if you take something and you lower it. Now, how is this thing giving me energy? Well, if I was cleverly designed, I could have a system of gears and levers by which I could, ultimately store energy in my little Prius battery or something like that, right? As this thing goes down, I get more energy, right? Those are the people that run the cross-country races. As they go downhill, they store energy in their and get more energy in their blood system, and then as they go uphill, they use that energy. We haven't gotten there yet. That would take some bioengineering. Okay, so let's have you guys try these. Whiteboard. Just go.